Okay, today guys, I'm going to be explaining hemoglobin's oxygen binding potential and the role it plays in pH and oxygen delivery. So this is the molecule that goes through your body and basically just picks up the oxygen into the lungs, and it's going to drop it off in the capillaries and the rest of the body. I'm going to show how it does that. So here's the basic structure of it. It's not the greatest photo, but you got the heme group. Which is basically a non-protein part that is very specific for binding to oxygen. The protein hemoglobin is found inside the red blood cell. That's what it looks like. It's composed of 4 protein subunits, each containing a heme group with an iron atom at its center, which is going to bind the oxygen. And the heme group is it's a non-protein. It's made up of it's hard for me to say, propofforin ring, which is a ring of 4 priol rings linked to a methylene bridge. The iron atom is located in the center of that ring. So rings, and you'll see more of the structure here, but essentially the most important part is the iron there. The rest is just kind of conformationally making it favorable to bind oxygen, minimizing hindrances or steric hindrance. Heme group and oxygen binding. So this heme group, and I've kind of drawn the end of it here, the deoxygenated and oxygenated form. That's the key component for binding oxygen, where the iron atom is. It's also reversible. So when it binds to the iron atom, there's a bit of a conformational change that allows the other 3 parts of it to change, which kind of helps the whole thing go well. I've kind of listed that at the bottom here. Here's basically the structure of it, and this loose oxygen is going to be bound over there. And you can probably imagine if there's a bunch of protons in this area too, as we'll see in a second, I mean, that oxygen would probably want to go to that hydrogen, or at least be tempted to go there, and a bunch of randomness in a system. Eventually, it might happen. The lungs have a slightly alkaline pH of 7.4, for much oxygen binding. These are all just reasons that why it even gets in the lungs in the first place. It's the pressure, for one. There's more oxygen, physical pressure, speeds up the reaction. Slightly basic pH, which means there's less hydrogens competing with this site right here. And that cooperative structure, which essentially just when one goes, the rest goes. So when it releases into capillaries, that oxygen goes away, goes to an H+ ion. So when cells are working, they release CO2 as a result of how the mitochondria works. So when there's more CO2 in the blood, the tissues cause the oxygen to release the hemoglobin. Essentially, the CO2 it can cause it to react with water, and it basically forms an acidic compound. I'm gonna skip. Yeah, so it's HCCO3 minus and H plus. I mean, essentially this reaction occurs, and that kind of favors this to happen. It makes the red blood cells at the capillary more acidic. That's a direct result of cells working, and the byproduct of that. And this hemoglobin is essentially taking that CO2, and it's kind of being the garbage man and shuffling it away here. It's another function of this hemoglobin, but this is we're talking about the specific protein here. And yeah. Let me just move on here. Okay. So yeah, I'm just going to summarize it here. Hemoglobin binds the oxygen in the lungs due to the high oxygen concentration and the pressure and the slightly alkaline pH. So not many pH ions, while the lower pH in the capillaries, due to the presence of more CO2 in the environment, promotes oxygen release from hemoglobin and into the cells. So that about wraps it up. I hope the visual aids were good enough for us here. Essentially, when you have cells working, you need to have a way for the oxygen to be released, and it just so happens that the byproduct helps them do so from the mitochondria. So that's about all I got here. Thanks.